From the University of Wisconsin-Milwaukee, the Science Bag, the television series where faculty members from university science departments share their special interests with you. And now, balloons that rise, clouds that fall, and air that crushes, forces in the atmosphere. With Jonathan Kahl, Department of Geosciences.
I know you're probably thinking that since tonight's program is being given by a meteorologist, there's only a 50% chance that anything you hear is going to turn out to be true. Well, I can assure you that tonight's show is going to be nothing like the weather broadcasts that you see on TV. For one thing, you have no remotes. You can't change the channel. But the good news is that maybe by the time you're done, I will have convinced you to think about air in a different way than you're used to thinking about. Air is strange stuff. You can't grab onto it, yet it's strong enough to knock you off your feet. You can't feel the air, even though it's pressing down on you with the weight of thousands of pounds. You can't see air, but you can see rain and snow falling out of it. You can't hear air, although sometimes you can hear the rustling of leaves or the crashing of thunder. In fact, we hardly ever even think about air, despite the fact that we couldn't live for more than a few minutes without it. Well, welcome to the Science Bag. Tonight's program is about air. I have a number of demonstrations here designed to illustrate different properties of the air. Some of these demonstrations are things that you can do at home using household materials like ping pong balls and balloons and newspaper. Other demonstrations, well, you might not want to try at home. And I think you'll be able to tell which ones are which. There are a number of books over here on the rack, all of them about weather. Some of them are for kids, some are for adults. Some are about experiments that can be done, illustrating different concepts involving weather. I'd like to start out tonight with a question. And in order to do that, I need to have an answer. So can I have a volunteer to give an answer to my question? Let's see. Okay, why don't you come up here? Okay, tell us your name.
Miles Caithan.
Miles, okay. My question for Miles is, what's in the box?
Air.
Air. I knew you were going to say that. Great answer. Let's give Miles a big hand. You know, that's the answer that I was looking for, but I was a little worried that you were going to say nothing, that there's nothing in the box. And that would not have been the correct answer, because there is not nothing in the box. There's air in the box. And Miles's correct answer provides a perfect lead-in to the first idea that I want to talk about tonight. Air is not nothing. Air is something. Now, when we study air, as meteorologists do, we have a little problem because air is invisible. We can't see it. It's hard to understand something that you can't even see. So we have to be a little sneaky and use indirect methods such as studying the effects that air has on certain things. So let me do a couple of demonstrations to illustrate a few of the effects that air has on other things. So here I have a piece of newspaper and a bowl of water. If I were to dunk this newspaper in the bowl of water, I think you all know what would happen, right? The newspaper would get wet. That's so obvious that I'm not even going to do that. Instead, I'm going to put the newspaper in this beaker. If you do this at home, an ordinary drinking glass will work just fine. And turn it upside down and dunk this into the bowl of water. And when I do that, I can pull the newspaper out, and it didn't get wet. The reason the newspaper didn't get wet is because there was air in between the newspaper and the water. And air is something. It is not nothing. And one effect that air has is that it can prevent newspaper from getting wet. Now I have another demonstration that illustrates another effect that air has, and I'd like to ask for a volunteer this time for this one. Let's see. Let's pick someone over here. Okay, why don't you come up? Okay, can you tell us your name?
Lisa.
Lisa. Okay, come over here. Now this is a bicycle pump, and the purpose of a bicycle pump is to move air. Usually the air is moved from the tube of the pump into a bicycle tire. This bicycle pump, though, is a little bit special because I put a whistle on the end of it. Now I want to demonstrate to you what effects some different things have. First, I'm going to demonstrate the effect that nothing has. So I'm going to send nothing through the whistle, and I want you to listen to what that sounds like. Hear that? Okay, now Lisa is going to move air through this whistle, and we're going to hear what that sounds like. So can you pump the pump a few times? Keep going. A few more times. Okay, thanks. So, see, don't go away, don't go away. So air, when it moves through the whistle, makes a noise. And it's a different noise than nothing makes. So again, a demonstration that air is something, it is not nothing. Now another reason that this pump is a little bit special is it has a valve, this little black knob here. And when I turn the valve, that causes the tube to be pinched. And that will prevent air from going through the whistle. So now let's see what happens when Lisa tries to pump the pump now. Okay. Okay, thank you. Let's thank Lisa. She couldn't work the pump because there was air in there. And since the valve was closed and the tube was pinched, the air was preventing the pump from going down. So air has another effect that we see. It can prevent a pump from moving. Okay, so air is not nothing. Okay. Well, one of the properties that things have, as opposed to nothings, is that they have weight. And air is no different. So that brings me to the next idea that I want to talk about. The atmosphere is just all the air around the Earth. The atmosphere is very heavy. Now, this is a little bit of an unusual thing to think about because meteorologists talk about lots of different aspects of air. They talk about the temperature and the wind and the rain or the snow, but they don't usually talk about the weight of the air. You don't usually turn on the weather broadcasts and hear them say that the air is going to weigh 30 pounds tomorrow. But what you do hear meteorologists talk about is pressure. They talk about whether the barometer is rising or falling. The pressure is changing. Air pressure is very closely related to weight because the pressure of the air is just the weight of the air pressing down on the ground. So air, there's a lot of air. It's something, it's not nothing. I want to show you that air is very heavy. So I have a demonstration for that, and I think I'll do this one by myself. This is a paint stick, or a paint stirrer. This paint stirrer is kind of larger than life. I made a large one so you could see it in the back. But if you do this demonstration at home, a regular paint stirrer that you might get from a hardware store will work just fine. Paint stirrers are great. They're one of the only things that you can get for free. Okay, well, if I put this paint stirrer on the edge of the table and take another piece of newspaper, make a ball, put it on the end of the paint stirrer. Now, if I slap this paint stirrer lightly, it's going to cause the ball to go up. Watch. The reason that happened is that the force, or the weight, on this end of the stick was greater than the force or the weight on this end of the stick. Now on this end of the stick, the force or the weight was my hand. On this side, the weight was the air that's pressing down, the weight of the air that's pressing down on this balled up piece of paper. Now I'm going to take another piece of newspaper, exactly the same, and spread it out. Oops. This time I'm going to spread it out without making a ball out of it over the paint stirrer. And watch what happens when I slap the end of the stick with the same amount of pressure. It doesn't go up. Well, it's the same piece of newspaper. It weighs exactly the same. The reason it doesn't go up is because now it's occupying a larger area. So that means that more air is pressing down on this newspaper, more weight. Okay? So air is very heavy. And in this case, the air is heavier than the force of my hand. All right, well, so air is heavy. It's very heavy. How heavy is it? Well, let's actually put some numbers to this. I have a short video I want to show you. Now, while you're watching this video, I would like to ask you to imagine a checkerboard. And imagine that our checkerboard is 12 rows by 12 columns, 12 by 12 squares. Now, the air pressure is about 15 pounds per square inch. That's the value of air pressure at ground level, 15 pounds per square inch. So if you imagine this checkerboard, which is 12 by 12, is exactly 12 inches by 12 inches, then that means there's 12 rows here, 12 rows this way. And if you imagine that each of these bars weighs 15 pounds, because that's what the pressure is, 15 pounds per square inch, then that means that over each square inch of this checkerboard, the air weighs 15 pounds. Well, 15 pounds isn't very much. We could all probably lift 15 pounds. But could you lift 15 pounds times 12 times 12? Well, 15 pounds times 12 is about 2,000 pounds. So that means that the weight of the air that's pressing on 1 square foot of ground is 2,000 pounds. 2,000 pounds. That's a lot of weight. Do you think that that's 2,000 pounds is enough to crush something? If 2,000 pounds were on top of you, do you think you'd be crushed? Well, I think so too, but 2,000 pounds is on top of you. See, look at me. I'm an average-sized person, maybe a little small even, and when I stand, the amount of ground that I cover is about 1 square foot. So that means that pressing down on top of me and on top of each one of you is 2,000 pounds of air. Yet, we're not crushed. That's kind of a mystery. So let's think about that. Let's see what it takes to crush something. Well, here is a can, a large metal can. Do you think I could crush this with my hands? I tried earlier, I dented it, but that was about all I could do. I think that if I pressed really hard, I might be able to dent it, but probably not more than that. If I put it on the ground and jumped up and down on it, I might dent it a little bit, but I still don't think I could crush it. This can here has been crushed. Now, how much weight or how much force do you think it would take to make that can look like this one? Can you imagine what would have to happen to that can to make it look like this one? Well, you don't have to imagine, because I have here a tool that all meteorologists use. And I want to demonstrate to you, I want you to understand what 2,000 pounds really means, what 2,000 pounds can do. So I'm going to whack this can a few times with this baseball bat and see if I can make it look like that one. Okay, to give you an idea of how much weight or how much force it really takes to crush something. You know, I have a better idea. Why don't I have a volunteer do this? Let's see. Why don't you come up? Okay, tell us your name.
Garrett?
Okay, this is Garrett. Garrett, do you like to play baseball?
Yeah.
Okay. So here's what I want you to do here. Hold the bat and don't do anything yet, please. Now, do you remember when I was slapping that paint stick, I was being kind of gentle about it? I don't want you to be gentle here, okay? I want you to give that can a few whacks and see if you can make it look like that one down there. Okay, go ahead. A few more. Okay. Good job. Let's thank Garrett here. Now, Garrett gave this can some pretty nasty whacks here, but it still doesn't quite look like this one. I think that it still has a way to go before being crushed. So I think we ought to ask Garrett's dad to come down here and give it a few whacks. Okay. Let's give it a couple whacks and see what you can do. Okay, that's enough. Thanks. Well, despite Garrett's whole family's best efforts, they still couldn't crush the can. Now, the atmosphere is very heavy. The atmosphere that's over 1 square foot of ground or 1 square foot of can weighs about 2,000 pounds. Now, 2,000 pounds is enough to crush a can, yet the can isn't crushed. The reason the can isn't crushed is because there is air inside the can. And air can prevent cans from being crushed, just as it can make a whistle, make noise, and do lots of other things as well. So I had a good idea. My idea is, why don't I take the air out of this can? If I take the air out of the can, then there's nothing that is preventing it from being crushed anymore. So I've hooked this can up to a vacuum pump, which is hidden behind the bench here. And this is just a pump very similar to the little motor that's inside your vacuum cleaner. It's not terribly strong, but what it will do when I turn it on is it will very slowly take the air out of the can. And when it does that, then there's nothing to prevent the 2,000 pounds of air that is over that can from crushing it. So let's watch and see what happens. This pump, as I said, is not that strong. It works kind of slowly. But the air is slowly being sucked out. And as that's happening, the can is feeling the crushing force of the atmosphere above it. Okay, so now we have a can that looks like that one. So the air is very heavy, and in fact, it is heavy enough to crush things like these cans, provided that you take the air out of them first. Now, since the air pressure is so great, and that means that the weight of the air is so much, that presents us with another problem. So in order to demonstrate that next problem, I have another tool that all meteorologists use. Okay. This balloon here, a minute ago, or a few seconds ago when I pulled it out of my pocket, it was soft and floppy. But now, it's tight and stretched. The difference between the way it is now and the way it was half a minute ago or so is that there is a lot of pressure inside this balloon, since there's a lot of air crammed inside of it. Well, I'm going to do a little experiment here. I'm going to make a small hole in this balloon, a small opening in the balloon. I'm not going to poke a hole in it. I'm just going to unsqueeze my fingers a little bit. And we're going to see what's going to happen. There's two possibilities. Either the air inside the room will rush into the balloon and the balloon will get bigger, or the air inside the balloon will rush out and the balloon will get smaller. We'll see which one happens. Oh, okay. It was as I suspected. Let's do it again and make sure it's not a fluke. Okay, provide a small opening. Okay, the air rushes out from inside the balloon to the outside of the balloon. Now, why does it do that? The reason that the air goes out from inside the balloon towards the outside instead of from outside towards the inside of the balloon is because the air pressure inside the balloon is very large. And it's larger than the air pressure outside of the balloon. And air will always try to move from areas where the pressure is large towards areas where the pressure is small. So air moves from high pressure towards low pressure. This is a little bit puzzling because air pressure is the weight of the air above the ground. Well, if air pressure is the weight above the ground, then that must mean that the air pressure near the ground is higher than the air pressure at higher altitudes, like on a mountaintop. Because if you're on a mountaintop, you're so high up that there's less air above you, because a lot of it's below you. So since the air pressure is high at the ground and lower at higher altitudes, then why doesn't all the air just whoosh on upwards, up towards higher and higher altitudes and escape off to space? Why do we have air at all? We saw from the balloon that air moves from higher pressures towards lower pressures. So why doesn't that work in the real world as well? Because air pressure is highest at the ground. Well, the answer to this riddle is that there must be something holding it in. So the thing that holds it in, that holds the air towards the ground and doesn't let it all escape, is the same thing that draws everything towards the Earth. And that thing is a force that's called gravity. So I can demonstrate gravity very easily with this ping pong ball. When I drop it, or when I release it rather, it doesn't go up, it goes down. And that's because the main force that's acting on it is gravity, and that pulls it downward. Well, let's see what would happen to this ping pong ball if two forces were acting on it, gravity and a force pushing it upward at the same time. I need a volunteer for this demonstration. Let's see. Pick someone from this side. Let's see. Okay. Now, this demonstration is a little bit dangerous. Do you like danger?
Sure.
Okay. Tell us your name.
Cassie.
Cassie. Okay. Cassie, let's see. You better put on these goggles here, just in case. Now, Cassie is going to operate a dangerous piece of equipment. And when she does, this dangerous piece of equipment, see how you turn it on? Okay, hold on to it. The dangerous piece of equipment will propel a stream of air upward. So this will create a force that is moving upwards. So go ahead and turn this thing on. I'm going to put the ball right in the stream of air. Now, the force of air is going to cause it to go upward, but the force of gravity is going to cause it to go downward. So let's see what happens as these two forces battle it out and see who wins. Oops. Okay. Thank you. So what you saw is the ping pong ball floating almost motionless, and that's because it was in balance. There was a force pushing it upward, and there was a force pushing it downward, and yet it didn't move. That's because those forces were in balance. Now, in the atmosphere, the same thing happens because you have this pressure force, that the same force that wants to make air go out of a balloon when you poke a hole in the balloon, that force makes air want to move upward, and yet you have gravity at the same time that makes the air want to go downward, and so those two forces are in balance. And that's the reason why the air stays, and it doesn't all just whoosh on out to space.
If you'd like to continue this program at another time, this might be a good time to stop the tape and take a break.
Well, this brings me now to the third idea that I want to discuss tonight. Clouds don't float. So far, I've been talking about air. Well, I think it also makes sense to talk about things that we see in the air, like clouds. Well, this idea that I just discussed, this balance of forces that causes the air to stick around and not just all blow on upwards out to space, that's fine for air. But what about water? Clouds, after all, are not air. If they were, we couldn't see them, because air is invisible. We can see clouds. We see clouds all the time. In Milwaukee, far too often. You see clouds on my shirt. Clouds can't possibly be made of air, because we can see them. Clouds are made of liquid water or solid water, ice. Liquid water and solid water, both of those things are heavier than air. So they can't possibly float. Because if I dropped some water here through the air, it wouldn't just sit here motionlessly like the ping pong ball did over the hairdryer. Well, I don't have to convince you of that. I think I can do a demonstration to show you this. The problem is that this is the part of the program where I'm supposed to climb up the ladder. And you know, I was really going to do this. I really was going to climb the ladder. But as I was preparing this presentation, I got word from the university officials that I can't climb the ladder because I'm not licensed to climb the ladder. So the university has provided someone to climb the ladder. And this fellow walking down right here is Al Zamora from University's Physical Plant Services. Let's give Al a big hand. And in a minute, Al is going to climb the ladder for me. And what Al is going to do if he survives it is he has a couple of water balloons up there, and he is going to release the water balloons from that metal chute at the top of the ladder, and we're going to see if those water balloons will float. Okay. Now, Al, why don't you go ahead and climb up there? clouds don't float. Clouds, after all, are not air. If they were, we couldn't see them, because air is invisible. We can see clouds. We see clouds all the time. Clouds don't float. Well, as Al's climbing up there and getting himself ready, I need a couple of more volunteers, because while he's up there, I have an idea that I might do something else. So let's see. Now, I need a pair of volunteers this time. Maybe a child and a parent type of volunteer. You guys will do just fine. Why don't you come up? Okay, tell us your names. Charlie? Paul. Charlie and Paul. Okay. Charlie and Paul, let's go over here for a minute while Al's getting ready up there. Okay. Slide aside a little bit, please. Okay. Well, in the true spirit of science, we're going to take advantage of the fact that we have this big contraption here, and we have Al up there to release the water balloons. And I'm going to do another experiment as well. Now, the first experiment is that Al's going to release a water balloon, and we're going to see if it floats or if it falls. Now, we'll see what the result is, and I don't want to suppose that I know what's going to happen. But just in case it falls, because that's sort of what I think, then I'm going to do another experiment at the same time. And that experiment is, we're going to time how fast it falls, how long it takes to fall. Because I think that a larger water balloon, Al, can you hold up the small water balloon? Okay, that's the small water balloon. Okay. Now, he has another larger one up there, which we won't show you just yet. I don't want you to leave. But I have an idea that maybe a larger, heavier ball of water might fall faster than a smaller, lighter one. So here's what I want you guys to do. Let's see, Charlie, I think you better put this on. Okay. Here, you stand over here. I'm going to get far out of the way. Charlie, behind you is a mop. Okay. I just want you to know where that is in case we need it. Okay. And Paul, I'm going to ask Charlie, not just yet, but in a minute, I'm going to ask Charlie to say 1, 2, 3, go. And when he does, Al is going to release the small green balloon, and we're going to see if it floats. Now, in case it doesn't float, Paul, I would like to ask you to time how long it takes to fall in the event that it falls. Okay? So this is start, stop, and then reset, because you're going to do that again.
Go, when Charlie says
From when Charlie says go.
until it's there.
If it floats, right. All right. Charlie, y'all zipped up there? Okay. Okay. All right. Al, are you ready for us?
Ready.
Okay, Charlie, do your stuff. Say 1, 2, 3, go.
1, 2, 3, go.
It fell. It didn't float. Okay, Paul, how long did it take?
1 1/3 seconds.
Okay, 1.33 seconds. All right, so that's one riddle that is solved. Okay. Water is heavier than air, so it doesn't float. Clouds don't float. They can't, because they're made of water and they're heavier than air. Now it's time for the second experiment. I have this idea that a larger drop of water might fall faster than a smaller one. So Al, can you show us what the larger water balloon looks like? Okay. Okay. All right, now we're going to do the same experiment again. Charlie, don't forget where that mop is now. And when Charlie says 1, 2, 3, go, I'm going to ask Paul to time it. And Al's going to release the balloon, and we'll do this second experiment. Everybody ready? Okay, Charlie.
1, 2, 3, go.
It's okay, Sean. Okay, now, before you guys go, Al, could you just sit tight up there for a minute, please? Paul, can you tell us how much time it took?
1.6.
1.64 seconds. Well, the small balloon fell in 1.3 seconds. The larger one took 1.6 seconds. So something's wrong here. Well, let's thank Charlie and Paul. Be careful, it's wet down here. Well, now there's two possibilities here. Either I was wrong and larger, heavier objects fall more slowly than smaller, lighter objects. That's one possibility. Or the other possibility is that maybe despite Paul's best intentions, his reflexes just weren't quite fast enough, because we're only talking about a fraction of a second here. And they weren't quite fast enough to time it exactly, and maybe I'm right after all. So I have another demonstration, because I'm not willing to give up my idea yet that larger, heavier objects fall faster than smaller, lighter objects. So as long as we have Al up there on the ladder, I have another demonstration. And what Al has up there is a platform with 7 styrofoam balls. The 7 balls range in size from about a foot in diameter. That's the largest one, and the smallest one is smaller than this ping pong ball here. Now, in a minute, I'm going to ask Al to release the lever that will cause those balls to fall. And I would like you to watch it very carefully. Now, you're going to have to watch very carefully, because those water balloons fell in just about a second or so. So these balls are going to fall very quickly. Now, this is what I want you to look for. If my idea is correct, that larger, heavier objects fall faster than smaller, lighter objects, then the larger ball should hit first, and the smallest ball should hit last. So that means that as they fall, if I'm right about this, that they should fall at kind of an angle, with the larger ball hitting first, the smaller ball hitting last, and kind of a line like this in between. So let's watch very carefully, because once the balls are down, I can't get them back up there. And we'll see what happens, and we'll see if I'm right. So Al, you ready? Ready. All right, I'll give you a 1, 2, 3, go. 1, 2, 3, go. Well, what do you think? Did it work? How many people think the larger balls hit first? How many people think the smaller balls hit first? There's some disagreement here. Okay, again, it wasn't conclusive. Well, let's thank Al for his help here. I am not ready to give up my idea yet that larger objects fall faster. So I'm going to show you a videotape, because I did this experiment earlier and I taped it. I made a videotape, and I'm going to show you that tape in slow motion. Okay. So you're going to see me up at the top of the ladder with the same 7 balls, and we're going to release them, and this is filmed in slow motion. And watch what happens. They fall, and the smaller ones are falling faster. But as you watch carefully what happens. The middle ones are catching up to the smaller ones now, and now the larger ones are catching up. And here, just before they reach the ground, the larger ones do in fact fall first. And in fact, you see this line that I was talking about, with the larger ones hitting first and the smaller ones, here's the smallest one right here, hitting last. Well, this is a little bit hard to see even when it's slowed down like that. So I'm going to show it to you again. There's another, I did this experiment a second time, and this time I used only 3 balls just to make things a little bit less confusing. And what happens is very interesting. As they fall, at first, the smallest ball falls fastest. The middle one catches up, and then after a few more seconds of this tape, the larger ball finally catches up, and you see this line, and the large ball does indeed fall the fastest. This is how we get the balls up there. Okay. Okay, well that's fine for styrofoam balls or for water balloons, but I started out talking about clouds here. So let me get back to the clouds. Now, the projector's all wet. Okay. Well, clouds, as I told you before, are not air. Clouds are water, liquid water or frozen water. So what I have here is a graph showing the speed that different size water drops in the air fall. Now, on this graph here, the first one I have, this first bar over here, shows a large raindrop. And large raindrops are about 5 millimeters wide, and 5 millimeters is a fraction of an inch. Large raindrops fall at a speed of about 30 feet per second. Now, 30 feet every second, that's a pretty fast speed. Now, the next bar shows an average size raindrop. An average size raindrop is about half the size of a large raindrop, an even smaller fraction of an inch, and that falls more slowly. Small raindrops fall more slowly still. Well, raindrops are a lot bigger than cloud drops. In fact, raindrops are about 1,000 times bigger than cloud drops. The size of an average cloud drop is only a fraction of the size of a pinprick. It's microscopic in size. And a ball of water that small falls very slowly. And in fact, here, you see that a large cloud drop falls only a couple of feet each second. An average-sized cloud drop, which has a red bar that is so small that you can't even see it on this graph, an average-sized cloud drop falls only 1/3 of an inch in 1 second. It takes 3 seconds for a cloud droplet to fall even an inch. Well, clouds are located thousands of feet in the air. Some clouds you might find at 2,000 feet, others at 5,000, 10,000, 15,000 feet. Well, if it takes 3 seconds for a cloud drop to fall an inch, how long do you think it might take for a cloud to fall out of the sky? Hours, days maybe, because they fall so slowly. And clouds do fall. They don't float. So the question is, what happens as they fall? Well, what happens to water when you leave it alone for a while? It evaporates. Just like when you take a shower, you will eventually get dry even if you don't dry yourself off. The water will evaporate. So clouds do fall, and they fall so slowly that they evaporate long before they reach the ground. Okay, there's another reason, too, that clouds stay up in the air. This reason, this second reason that clouds stay up in the air despite the fact that they don't float has to do with wind. Now, when you talk about air, tonight when I'm talking about air, I've been talking a lot about upward motions, about the weight of the air pressing down and the pressure force moving upwards. Well, when we think about air, one of the things that most obviously comes into mind is wind. And wind is the horizontal or sideways movement of air. What I want to show you now is that horizontal or sideways movements of air can also keep clouds in the sky, even though they're falling. When you have winds that come from two directions and kind of meet in the middle, that creates an upward moving current of air, just like the stream of air coming out of our hairdryer. And we saw that the hairdryer could hold a ping pong ball up in the air, despite the fact that gravity wants to make it fall. So converging streams of wind can do the same thing. So I have a demonstration to show you that. In this tank here, I have 3 compartments of the tank. And I just have clear water in the middle. And on the left side here, I'm going to put in some yellow or greenish water. And on the right side, I'm going to put in some red water. And as soon as I put the red water in, I'm going to lift these gates, which will allow the yellow and the red water to stream in towards the center. And what I would like you to do is to watch what happens in the middle. The yellow and the red water, now, this is water. I'm supposed to be talking about air here. Well, water is a fluid. And the thing that makes a fluid different from something that's solid is that it's free to conform to any kind of shape. Well, air is a fluid also. Air also can conform to any shape. So we can really understand how air works by watching how water works. So let's just imagine that this is air in here, because air works the same way. So as you watch the red air stream into the middle and meet the yellow air that is streaming into the middle, I would like to ask you to watch what happens. Now this is going to go very quickly, probably even more quickly than the balls falling. Okay, watch what happens. Okay. Did you see what happens as they mix? Did you see the pattern of air movement? I bet that you probably couldn't see it because it went really fast. But luckily, I have a tape. So let's take a look at this tape. Let's see if I put the right one in this time. So there's the center compartment. And now the red and the yellow wind is streaming together, and look what happens. When they meet, they rise upwards, and they create this upward moving stream of air, just like you saw with the hairdryer. So that often happens in the atmosphere where you have clouds, and if there happened to be a falling cloud above that center upward moving point, then that would help keep that falling cloud in place. Now here you're going to see it again, and there's another thing I wanted to point out. As you watch the water go up, remember that what comes up must come down. And as it goes up, it reaches the top and it spreads out and comes down at the sides, so that this area on the side and this area on the side are the last parts of the compartment to gain any color as the air comes up, spreads out, and moves down. All right. Oops. All right, well, a talk about air wouldn't really be complete unless I said a few more things about wind. So wind, which is that horizontal movement of air, which is very common to our everyday lives, just happens to be something that is extremely easy to measure. And the instrument that meteorologists use for measuring wind speed is called an anemometer. Now I have up here a real professional quality anemometer, but I want to show you in the last few minutes here that anemometers are very simple devices that are easy to make. So I'm going to build one for you here. And as you leave tonight, up at the top, some of the handouts describe how to build an anemometer just like this one. And the papers also describe how to calibrate this anemometer. In other words, how to figure out exactly how many turns of the cups translates to how many miles per hour. Okay, this is the tricky part here. I have to puncture the nail without drawing blood. Okay. Okay. Ta-da. Thank you for coming.